Okay, I see Sarah now. Sounds like somebody else just logged in. Okay. Let me turn the light off. Okay, we are doing the last section of notes for your test. Tomorrow's review. I did create a Kahoot. There are no embedded images. There's no opening video yet. I haven't gotten that far into it. Yes, the paper version's up here. Yesterday was the composition, and there were a lot of, for lack of a better phrase, cousins of each other rocks, like basalt and gabbro are cousins of each other. One is intrusive, one is extrusive. Rhyolite and granite are cousins of each other. One is intrusive, one is extrusive. Today we're going to talk about how magma plays such a central role. Did she take one of these? She did. She took Miss Castleberry. I have some larger geodes that are my daughter's that I told my coworkers they would have first dibs on. I got my geodes in for you guys last night. They're a lot smaller than what I'm used to opening, but considering they were less than $1 a pop, it doesn't surprise me. Anyways, what we're doing today is we're looking at the role of magma, specifically in how igneous rocks are produced. To unfreeze my screen, that would be wise. And for the opener, that I do not have. No. As magma lifts, as it goes closer to the surface, closer to the crust from the mantle, it does start to cool. It's still molten. It's still going to kill you if you try to swim in the magma. You know, don't try to swim in magma or lava. You're going to die. But what's different between your rocks that crystallize, not minerals, but your rocks, things like olivine, that crystallize very, very deep in the earth, versus ones that crystallize at higher depths, which is closer to the surface, closer up into the crust. What's the major difference between deep rocks and more, I guess shallow is the right word for it, the more shallow rocks that are within the crust? Considering that it was talked about yesterday when I was not in here. No, they're all intrusive. They're still inside the earth. What's the difference between the ones that are very, very deep, like olivine and gabbro, and then the ones that are a lot more shallow, more towards the crust, things like granite and quartz? What's the big difference between the two? Besides they have different names. I hear that. The difference in what? The what? Okay, so it's the chemical composition. The closer now which one has more silicon or silicate in it? The upper levels, the crust, or the lower levels? I don't want to turn this class into a chemistry lesson, but if I take a look at my periodic table, I have here handy dandy. Silicon, okay, its atomic mass is 28. Your heavier elements have more calcium. Its atomic mass is 40. So your deeper elements, they're more dense. So they have a specific chemical, more of a specific chemical composition. The two big words that were repeated yesterday were mafic and felsic. Felsic comes from feldspar and silica. Felsic, they literally smash the two words together. Mafic comes from magnesium and iron, which it's Latin. There's so much Latin in this section of notes right now. That's iron is ferrum or ferrous. So literally magnesium, ferrous, thick. So mafic. Those are much more dense. They have a much higher melting point, which is why they crystallize out first. And your first one to crystallize out, not gem-wise, don't think gem, which is rock, is called olivine. We're going to take a look at something called Bowen's reactive series eventually today, and it's in Canvas. You need to know how to read that map. Not like a map of the United States map. Going from interior, which is the top, to the crust, which is the bottom, which does kind of confuse some people. There are paper notes up here in Canvas. Magma, there are different types of magma. There's different sections of magma, there's different portions. We talked about that a couple days ago. There's the, oh, I hope I'm not muted. There's the liquid part, which is called melt. There are the solid parts, the silicates, more often than not. And then there's those volatiles. Let me just double check and make sure I'm not muted. Oh, and I've got more people online. I'm real quick. Do what?
Leaf blowers on this little thing that moves but it's really good.
Okay. We have time, you'll have to show me. Okay, I don't know what I heard, but it was not people online. As you go deeper into the earth, it does get hotter. Every kilometer going down, which is less than a mile, but every kilometer you go down, it increases, give or take 25 degrees Celsius.
So if we
that would be our best chance. It's warmer. Now, I don't know how you're going to grow plants without some type of sunlight, whether it be natural or artificial. Natural won't happen because it's nuclear winter. Yeah. I don't know if you've ever seen like doomsday preppers and whatnot, but people build their underground bunkers and they have some type of a power source that is going to create artificial light so they can grow their own food. In fact, I had a neighbor that put one of those things underground right before Hurricane Harvey. I always wanted to ask the Owens if it flooded. They're supposed to be flood-proof, but I don't know in the case of that hurricane if it was or not. They were like crazy neighbors that had not one but two cannons that they would shoot on a regular basis on their property.
That's so cool.
It is very cool. They also had a bunch of those axis deer, and they had a doe that was albino.
Oh.
Yep. They were. No, they didn't shoot her with the cannon. Goodness. No, they didn't go put deer. No, it was a breeding thing because they had that albino recessive gene. No. Oh,
They shoot no good deer with the cannon. Had a free cannon.
I swear, cannon hunting. A new section of hunting. So you've got rifle, you've got bow, and then you've got cannon as an alternative. I swear. Anyways, your rocks precipitate out. It's a chemistry phrase, but they go from the molten state to the solid state depending on their chemical structure and their melting point. Once it goes from warm enough to cool enough, it's no longer molten and it turns into rock. If you have any kind of extra heat, whether it be pressure, whether it be depth, whether it be stress, whether it be torque, it can cause these things to remelt. And we are not doing metamorphic rocks until after Thanksgiving. We are specifically focusing on sedimentary. Or not sedimentary, igneous. Pressure. You increase the pressure, it's going to increase the amount of temperature it takes to melt, which actually increases the melt point. Hold on, yes, increases the melting point. So the deeper we go down, the more temperature is necessary in order to change that from rock into the molten state or liquid. When I say liquid, don't think water. In this case, it's magma, it's not water. If there is enough pressure, it's going to stay solid. If there's not enough pressure, then it's going to start melting. And I have all different kinds of images, and I can't remember if I put them on the canvas thing. Oh yeah, I did. I put a lot of images on the canvas thing. Well, I mean, it's been molten before. There's no reason why it can't be molten again. Well, I mean, that would be really bad for us. We won't survive, but It gets hot enough, even your thermophiles, your extreme bacteria, the ones that really, really, really love heat, they'll want to. You have bacteria that's at over like 400 degrees, and they love it, and they thrive on it. There's shrimp that are in over 400 degrees temperature water. It's that pressure that essentially keeps you from cooking. In fact, if you took them from the depths of the ocean to the surface, they'd essentially explode. They can't survive without the pressure. Volatiles. These are gases that are suspended in said melt. The big one's water vapor, but it could be other things. Carbon dioxide, sulfur dioxide, hydrogen sulfide gas. But if you have volatiles that are present, it's going to cause the rocks to melt at the polar temperatures. That's one of the reasons why the oceanic lithosphere keeps recycling into the molten state, because of the presence of water in the ocean rock, the ocean crusts, the ocean plates, whatever. Lithosphere is the proper phrase, but it's the same thing as a plate or a crust. And I'm pretty sure I put this picture, yeah, I did, it's on the next slide. Put this image into the notes and onto your canvas, but your saturated ocean rock or sediment, it's more dense, it sinks into the asthenosphere, that conveyor belt that we talked about last 6 weeks, and it melts at a lower temperature than the drier continental crust does, which is less dense. And it, oh, my phone is blinking right over there. I guess it rained on the sun. It's what causes your oceanic lithosphere to keep recycling. Much more than your continental lithosphere. It floats, it's less dense. The silica has a lower molar mass than calcium does, which is what forms deeper into the earth. It's one of the first ones to precipitate out or settle or form from the magma state. Go from magma to rock. I'm pretty sure I put this image on this. I did. Okay, so we have, if I can get my, there it is, there's my cursor. So we have the magma that's trying to come up from inside the earth through the rift or the bridge, which we'll talk about this stuff after Thanksgiving break, which is not, we're not there yet. And so this is off to the side. This is essentially how volcanic islands are created. Eventually there's enough where it keeps going up and up and up until you have things like Hawaii. But your oceanic lithosphere is going to subject or subvert down underneath the continental. So this is more your granite. This is more silica. This is a lower molar mass. This is your wet oceanic lithosphere, and it will end up going underneath. You've seen a couple different images besides this one. We're eventually going to have a section with volcanoes. We've been talking about volcanoes because they help bring that magma up to the surface in the form of lava, and therefore it's exclusive and not intrusive. Intrusive is inside the Earth's magma, exclusive is outside through the volcano. But you can tell a different volcanic flow if you have multiple volcanoes in the same area, which specific volcano that rock came from, the basalt or the obsidian or the pumice, because each volcano has a slightly different chemical fingerprint. You tell the volcanoes apart, not by the basalt, not by the obsidian, but the trace elements, the rarer elements that are present. They have their own specific column type. What percentage are they present? And it's controlled by the different chemicals that have been molten into their magma pools underneath them. So it's not necessarily the silica, it's not the calcium, it's not the iron, it's not the magnesium, that's all there. It's the rarer elements, the trace elements. We'll have somewhere, I don't know if it'll be after Thanksgiving or if it'll be next 6 weeks, we'll have a volcanic meeting. It's not there yet. All right, Bowen's reaction series. You have to know how to read this thing's map. What it does is it shows you the order that different types of rocks precipitate out. What's going to be the one that does it first, which is at the highest temperature, which is deeper in the earth. Now it does sort of flip this thing that you guys would think upside down. Deeper in the earth is on the top. Towards the crust is on the bottom. It's not, I mean, I know that's not the way we think of it standing on the surface of the earth, but that's the way that this map, this chart is put together. Oops, let me get backwards. I thought that was one there. And they're going to crystallize out according to their very specific melting points. It depends on which chemicals are present as to which type of rocks are going to precipitate out first. Other people pay that. Let me check on some of this. I have a lot of people that are not here. So tomorrow we are reviewing. I did make a Kahoot. It's not super fancy, like, oh yeah, I got more people on here. It's not fancy the way that some of mine are. If I have time, let's see, Natalie. If I have time, I will start embedding stuff. But right now there are no images. It's just the annoying Kahoot stuff. Sorry if my computer's, oh, I just made it worse. There, I stopped it. That rumble that y'all are hearing online, that is my fan. I think my bearing is going out. I need to try some compressed air and see if I can't fix it, but I can't stop that weird rumble that's in the background from my computer. I don't want to actually take it apart and potentially shock it and fry the board, so.
No.
Yeah, that would not be good. I've actually done that accidentally before I learned what an electrician's bracelet actually was and how it worked.
What is it?
It keeps you grounded so you don't shock the components just from our natural. It's just like a metallic bracelet that goes on you and it keeps you from your own electrical charge shocking the sensitive components inside a computer. That's a thing. Yeah, I fried a brand new motherboard that I was putting in my computer, my desktop, long time ago, maybe 15 years ago. Yeah, I learned a very valuable life lesson that day. What an electrician's bracelet was. Yeah, no, I mean, it wasn't. That's the thing that's nice if you build your own computers, you can just plug and play, and it's a lot cheaper if you do make a mistake like that, that you're not replacing the entire unit, it's just that particular part that you fried. But yeah, I don't want to do that. That's school property. That's not my property. All right, this is Bowen's reactive series map. So up here at the top, this is deeper in the earth. Okay, it's like it's upside down. It's inverted. And as we go down, we are going closer to the crust. So we are cooling as we get closer to the crust. And your very, very, very first rocks to materialize, the very first one is called olivine. This has a very high iron and magnesium content. It's very, very, very calcium rich as the top. And as we go down, we become sodium rich. And then eventually we get to our silicates down here in the crust. So olivine is your first. This is what we call ultramafic. Very, very, very rich in magnesium, iron, and that's pretty much it. Pyroxene, this one's going to have a little bit more calcium than olivine. And as we go down, we're switching from calcium into sodium. There are different types of mica. These are the things that are very flat, and you can lift off layers and flat sheets, which is what we call cleavage. Biotite is very, very, very dark. Muscovite, this is very, very, very light. They still do the same thing. They're still mica. It just has to do with how much iron is present. If there's more iron present, then it's mafic, it's darker. If there's little to no iron present, then it's felsic, which would be your muscovite. And they're much, much lighter than less dense. So this map, you guys have it in Canvas, essay map, chart, whatever you want to call it. Down here on the bottom, this is your felsic stuff. These are your granites. Up here are your mafics. And these are your darker things. And your gabbro, this is something that was yesterday's. Gabbro is the internal, the intrusive part The salt is the extrusive part that comes out through the volcano. They have the exact same chemical composition. The internal one has the coarse grain. The external one has the fine grain, but it's the same thing. The same thing happens between granite and rhyolite. Granite is the interior part, the part that makes up mountains. Rhyolite is the less common surface version. Very few things turn into a solid inside magma. Very few things, whether they be minerals or they be rocks. Minerals are just very, very specified rocks. You think of those as gemstones, like a crystalline structure. They tend to be a lot prettier. But olivine and pyroxene, those are the two rocks that are actually present within the magma. As you go closer to the crust, which is what it showed on the previous slide, other things are going to materialize or crystallize out. Ooh, I probably should take like attendance, like in-person attendance. That would be honest. There are different types of magma, which I think is actually on a different slide. But the differentiation just means as things are, they're going to settle due to their density, and things that are more dense are lower, which is deeper in the earth, and things that are less dense are more towards the crust. Okay, Dylan is online, Jimmy's here, Alex is here, Esau's on, wait, I think Esau's on there. Yes. Alex, is that you that I'm hearing? Turn that off. Camera I do not see.
So is quartz the last to crystallize?
Yep.
He's looking at this map.
Yeah, it's like inverted. It's upside down. The crust is at the bottom and the interior of the earth is, so if it helps you, just think of it the other way around. It's just the way that Bowen created the map. I know it looks like it's upside down. It's not. It's just the way that it's inside at the top and then the surface at the bottom. I didn't make his reaction series. I just know how to read it. Assimilation. You've got different types of magma and rock that end up combining to make something new. And there are different types of magma. So I've got a picture on the next one, which I don't know if I gave that to you on the slide or not. I did. Oh, no, not the next one. I have a different one I can you. I don't think you guys have this one. You have, in this particular case, this is the original one. All three volcanoes are going at the same time. This is earlier on in time or further back in time, however you want to say it. Picture B, one of your volcanoes has actually died. It's lava tube. It's no longer able to be powered by this ball of magma. Eventually, they do go extinct. They only have so much fuel. Their fuel is magma. And as they get smaller and smaller, their silica amount increases. And so this last one, only the central volcano is still going. The other two have gone extinct. Their lava tubes have died. And this actually has the most silicate. This is the most viscous of the magmas that are present. Oops, let me go backwards. I thought there was one more on there. So the amount of silicate or silica, the same thing, that's present, changes how viscous or how thick your magma is. The more silicate that's there, the older the volcano is. Like I said, you can tell these things apart by their chemical fingerprints. You can have two different magma centers that merge, and that creates a whole new chemical composition. And so when we talk about volcanoes a lot, we have not gotten into a volcano unit yet. Yes, volcanoes are just how we bring the igneous rock to the surface, so we have to talk about them right now. But if they mix, whole new chemical composition, which is the picture that's on the next slide. So with this one, over here on the right, the two different magma bodies, the two different pools. Like I said, when I keep using these words, you think of water, but it's not water, it's magma. But if they do mix with each other, before that happened, this particular volcano had a very specific chemical fingerprint. And once these two mix, then the subsequent outer layers, because it goes on the top and then it settles, and then it goes on the top and it settles, it had a different chemical fingerprint. And we dig through the basalt, which is what it's called on the surface of a volcano, you can see back in time how long ago that occurred. And it has to do with how much of the silicate is present. Partial melting. They don't completely go molten. You've got suspended solid particles, whatever said solid particles are. We have different type of magmas. Basaltic, you've got very, very, very deep. Ultramafic is the deepest of the deep. And then you have mafic, which is above that, the gabbro and the basalt. And you've got your intermediate above that. And then you have your felsic, which is your crust. This is what happens in Hawaii. Your active volcanoes, your very active volcanoes that are constantly spewing out lava, they're settling down the basalt, which comes from the center of the earth. In the earth, once again, it's called gabbro, large crystals. On the earth's surface, same exact chemical composition, but because it dries and it cools faster, it's called basalt, and it has very, very fine crystals, but they are the exact same thing. It's just one is intrusive, gabbro is intrusive, basalt is extrusive. You know, if you've ever heard the phrase, the ring of fire.
Or the song.
No, not the song. I know there's a song that's called that too. Yeah. But it is an actual thing that goes along the edges of specific ridges or different plates in the ocean. Very, very, very active volcanic area. Like I said, I don't know if we're going to get into volcanoes in 6 weeks or not 6 weeks. I have not built my plate tectonic unit yet. I get to do that every Thanksgiving break. Woo! Like I said, 3 major types of magma. The first one that we talk about is basaltic, from deep in the mantle. The next type we talk about is the intermediate, which is andesitic. It's a combination of the basaltic, very, very deep, the super iron and magnesium, the ultramafic. Once again, mafic, magnesium and iron, ferrum, mafic. That's where that comes from. But it's going to combine with more of the felsic magma, the granitic magma, which is towards the top, which is a lot thicker, more viscous. But if they mix with each other, it makes an intermediate. It's somewhere halfway in between, which we call andesitic with rock. I think there is another slide after this next one, and I just did not print it out on my particular paper copy. The last type of magma that we're going to talk about is the one that forms with the granite, or actually the granite forms from it. I just said that backwards. But granitic magma is the most viscous, it's the thickest, it's the slowest moving. It is the coolest of the magmas. It's still molten. This is the type that forms what we call pegmatitic or pegmatite, the ones that have the very, very, very large crystals in them. I double checked through my igneous sample boxes back there, and the one that I did show 2 days ago, the pegmatite that I had actually had the largest crystals within it. When you see your big portions of silicate, and then you see very, very, very large crystals that are interspersed within them, whether they be garnet, periodite, all different kinds of minerals. We didn't go into every specific type, but we just don't have the time to go over hundreds and hundreds and hundreds of different minerals and gems. let me see if I have another one on here. Let me freeze you guys. Let me look. I thought I did. I don't. Okay, this is the last one. Let me double check online, which now I see more people. Okay, I don't see Kaden. I don't see Taylor. I see Erica. I see Neil, I think was online. Don't see Cameron. I don't see Mauricio. Okay, so let me go over one more time. Let me refresh my canvas in case somebody turned something in. Last 40 minutes on computer, you can do it. Let's see here. So Mondays, the 16th. Okay, Alex, Monday, still neither part or the opener from yesterday. Otis, the opener from both days. Caitlin, online, the assignment from Monday and both from yesterday. Caden, the opener from Monday. I got the one from yesterday. Okay, and then yesterday, both from Erica and the opener from Monday. Got Dylan's opener there. Where am I at? It's Erica. Cameron, both from yesterday. I got Mauricio's opener. Colton, both from yesterday and the assignment from Monday. And y'all, the assignment is shutting. It's shutting today. I'm about to put, this is the wrong paper. I've got too many dang paper grade books going at the same time now. Tell you what, let me turn the light on. I can't stare at my screen with the light off. The glasses on because of my headaches. Okay, so from Friday, which I'm about to put probably 3 different grades into the grade book. Okay, so I'm just double checking it and making sure I didn't have one turned in. I am about to put a bunch of stuff into the grade book. Mute my mic.